everybody. Wow. Thanks for coming out. I guess you're going to have to listen to me for a little bit. Yeah, I tend to feel like I'm in the graphics hacker mood today. So what I do when they let me out of my cage, to come to here is I try to explain what the Chrome graphics team and basically the Blink engineering team that works on smoothness, what we're trying to do, what we're thinking about. There's sort of this chasm between us implementers and the real world because, like I said, they don't let us out of our cages. I've been working on the graphics stack in Chrome for about 4 years, and we've originally titled this The Pursuit of 60 FIPS Everywhere because we've been trying to get 60 FIPS on MacBooks, 60 FIPS on Android, 60 FIPS on old Windows XP machines, and that's a nightmare. And we've been trying to do it when you have some old nasty site, say cuteoverload.com, which is just a pile of animated GIFs, and we're trying to make that 60 FIPS. And then at the same time, we're trying to make some nice mobile apps that people are making that are gorgeous run at 60 FIPS too. And about last year, we started thinking, this is kind of crazy. We're putting a lot of energy architecturally into dealing with sites like Qt Overload. And we're not thinking a lot about mobile, or we're thinking a lot about it, but when we look at our folks who are trying to make mobile content, we started noticing, wow, this hurts. These people are in severe anguish. And so what we decided is, let's really double down on this mobile story. How do we make 60 FIPS of mobile content an achievable and sort of reliable reality? And that's been a bit of a journey over the last year. We really started refocusing and saying, no, that's a terrible desktop site. Screw it. Let's make mobile really amazing. So there's a graphics stack talk. So no graphics talk is going to be complete without mentioning the layers word. And so what I want to do is do a really quick, really quick crash course on layers, and then move on to what we're thinking about rendering in 60 FIPS in the future. There's a lot of material up on jankfree.org that you all can go read. There's a great talk by our Paul from I/O of this year that sort of explains how to get 60 FIPS on all the browsers, using layers, using things like will change, using transforms. I'm going to do a short form of it, but if you really kind of feel blown away by what I end up talking about, go to Jankfree, check out those talks. They really put it in perspective for you. So layers. These are two pictures from Polymer.org content. The left is the quiz app, the right is the paper sampler. And this is the way the browser sees those pages, tilted using our tool called Frame Viewer, in order to see the layers in the page versus what the user sees. What the browser is doing every frame is it's looking at your DOM anytime you change it, and it's going, well, that's scrolling, and that has an animation on it, so I think they're going to move that in the future. It's sort of guessing. And then what it does is we sort of assume that painting and the rendering in the HTML stack is going to be horribly slow. And so we take a picture of whatever part of the page we think is going to move around together. We take a picture of it. We call that a layer. Think Photoshop layers. And we shovel that off to the GPU, and we keep it there. And so, unsurprisingly, if you go and muck around with an element that has been lucky enough to get a layer, and you start moving it around with just two properties, transform and opacity, if you just do those two things, then you're hitting the absolute fastest path that a browser has to moving something around. But there's this whole problem of, well, if you have a layer. So in the yesteryear, there were a lot of hacks. Everybody's seen the WebKit transform translate Z0 kind of incantation, which is exactly content-free. It means nothing, right? In the sort of spirit of say what you mean, what we did early last year after realizing that this whole thing is a mess, is we worked with Mozilla, or more appropriately, Mozilla worked with us to create this will change spec. And what happens in the will change spec is you say to us, I'm going to change this element's left, or I'm going to change this element's transform. And then what we do is we factor that into our calculation of what should get a layer. And then based on that, you usually get what you request. So if you hint something as having a changing left and it's big, you'll get a layer. This is really, really important for performance, as you can kind of imagine. If you don't hint the browser about what's going to change, then you get basically a flat world. Your whole DOM becomes one layer, and anytime anything starts moving, either you'll get lucky and it pops out and it becomes its own layer, or just it submarines through and the whole layer starts repaint storming and kittens cry and you don't go to space. Anyway, with will change, everything pops out to its own layer and goodness results. So this is one of the Polymer demos, and the thing that I wanted, I'm not going to do an extensive demo of this, but what characterizes sort of these demos is that they're nice and responsive, even on your phone. You know, I don't know what I'm typing here, but each one of these things that's moving around as I do it, you can guarantee it will change to the gills. What we're doing is every single piece of it is annotated with the will change annotation that best fits that type of motion that it's going to undergo. So I actually want to show you a little trace here of that in the actual frame viewer. So you saw those things that I was showing before. This is sort of how the user sees it, not tilted obviously. And this is how the browser sees it. Each one of those is a layer. And so if we advance through time, what you'll end up seeing is this yellow dot should grow, you know, after a stall to give me a heart attack, right? So, you know, this yellow dot grows and you see the whole rest of the world is completely stationary. Just this yellow dot is growing. And what you'll see at the end is there's that button, see it appearing? And then finally, the whole thing settles down, all the old DOM goes away, and we've got our final image. And that's a really good scripted animation, or not scripted, but coordinated animation where we've got everything coming in nice and smooth. Each layer is being transformed. It's 60 FIPS, happiness results. So layers, they're your friend, will change, super important. Hop over to JankFree for a lot more information on them. But what I really want to talk about today is why? When was the meeting? I missed it, where we sat down and we said, the way that you will be 60 FIPS on the web is through layers. And the way that you will make things fast on the web is by turning off all the web and having two properties that you can touch, translate or transform and opacity. Right? I missed that meeting, but man, that's a weird trade. Right? We've got all this great expressiveness in the web and we can only use two properties. And now if you ask around, you'll get a lot of answers for why this is. I'd like to give you my personal interpretation. I'm almost certainly wrong, but here goes. We browser implementers make our bread and butter from browsing websites, just plain old websites. You've all been to probably a dozen websites today. Sort of mundane, you know, maybe they were mobile optimized, but the vast majority of page views aren't. So they're these big sites that are designed for, you know, a big, powerful computer that's probably plugged in, and you're shoving it into your tiny little phone. And you're asking it to load quickly. You're asking it to scroll, even while it's still loading. Maybe you're going to pinch it so that you can tap a link and move on. And this has been the focus of browser vendors since these mobile phones came out. So Chrome was madly, you know, our team was madly just trying to make Chrome a decent web browser when viewing these pages. So why is this a problem? I took the Meetup desktop site and I shoved it onto a Nexus 5 and I profiled it. And the way I profiled it was with DevTools these days is coming with a new version of the timeline. This looks like plain old DevTools, but in the Experiments tab, there's now this fancy little thing called Timeline on trace events. And what that does is it gives you this button, and then you have about tracing type displays and about tracing type data right in your thing. Now, why does this matter? It makes it really easy to compute a table like this, which says during this period of time, this is exactly where your time went. Now, when you talk about smoothness, like when you talk about page load, you care about how much time is going where, but we don't have a network to contend with, so all we care about is how much CPU was being used right now and how do we make it smaller. The Meetup desktop site has literally 2,000 milliseconds of page load activity. And then even when it's static, even when it's just completely, you're not touching it, and then you just scroll it up and down, it does another 250 milliseconds, or whatever, 190 milliseconds of work every second when I scroll. I don't know what it's doing. It's doing some jQuery thing. But like you'd think nothing's changing, right? I go to this stupid thing and I scroll it up and down. It's not changing. But that thing is literally using 150 milliseconds every second to do something. And this is the world that a browser vendor comes into, which is lots of content that people really need to see, right? But a web page that either because it's loading or because somebody's script is having a bad hair day, it is unresponsive. So it's not acceptable for us to just have you, when you go to this site on your phone, just be completely unresponsive, like, oh, sorry, jQuery's thinking you can't scroll right now. Layers are the defense mechanism that we came up with to deal with an adversarial web. Let me do a demo to try to explain this. So bear with. We've got, everybody can learn my unlock code. We've got a simple page that is already got the checkbox. We've got a simple page that scrolls up and down. This is a simple demo, okay? Would we all agree that this is mostly smooth, right? It's sticking to my finger-ish. And then I'm going to press this jank button. And what the jank button is going to do is it's just going to do a set timeout that literally just pegs the JS for, I think it's 200 milliseconds randomly. And this is to simulate that sort of situation of the jQuery thing kicking off and being cranky. It's still smooth, right? What this is doing is we're using these layers to compensate for the jank and basically hide the fact that the page is being evil from you so that you get a good experience. And if you don't believe me, we can measure. Pop open this, take a timeline recording, and I'm going to pop over to to my screen. Hands going everywhere. This is the trace of what this poor app is doing in JavaScript, right? A 300 millisecond jank, but it was completely smooth to my finger. Okay, so I'm a Chrome hacker, so I now have to put up an architecture diagram because we've gone a whole, 5 minutes without one. This is the grossly oversimplified way that I see most web browsers existing last year, and really this year too. The composite step sits at the end of the pipeline. That has your layers. It also receives all the input from your finger or from your mouse, and it drives the screen. And when you scroll, it receives the input, updates the layers, and directly drives the screen. And the whole left side, JavaScript getting the on-scroll, recalc, and layout running in response, maybe your set timeout firing and changing the div and doing a background or whatever it is, all of that can go super, super slow and will still scroll, right? So we've optimized really, really hardcore in the direction of make that scroll responsive. There's this sort of trade that we've made implicitly in hyper-optimizing for smoothness, which is you don't really reliably find out about the fact that we've scrolled the page. Sure, you can listen to on-scroll, but it's not prevent defaultable, right? It's kind of late, right? If you try to do something in response to an on-scroll and position something, then everything sort of jitters around. You don't get any notice of like touch events once scrolling begins. It's all just sort of bolted on. Like we sort of send a little message over from the compositor side of thing all the way over to JS saying, hey, we scrolled if you cared. But we were 60 FIPS. And this is the architecture we have. And so there's this value proposition that we said that was, we gave you 60 FIPS, aren't you really happy? And having worked on this architecture and getting it working, we were pretty darn excited that we could give you 60 FIPS on these terrible devices. But what we're saying in exchange is if you want to do anything as an application that's compelling, you want the fancy drawer or the pull to refresh, you must represent all of this as a CSS animation or as scrolling. If you just remove the architecture diagram, because those are boring anyway, and you look at these two things together, you kind of see that there's this dissonance. This is not a great value proposition. Give me a browser that maybe isn't 100% efficient, but for the love of God, doesn't do this crazy stuff. We want a rational web browser because that's the one that empowers developers to do great things. And this weird thing with the scroll bypass that goes back to the sometimes blah, 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 that nobody understands except like 3 Chrome engineers and a couple at Mozilla, et cetera, it doesn't cut it. So we had this whole crisis of faith last year, and we shouted at each other in a googly way, so everybody was smiling, and then we decided, okay, let's do some stuff. Chrome 37 really is, we've been making changes on trunk, so Chrome 31, 32, 33, all of those have come out with little bits of improvements. 37 is where a lot of things just sort of happen to come together, and so it's a very exciting release for us, in as much as Chromies get excited about a particular revision. We think it's a lot better. And I try to do a laundry list of things that change it. And the thing that I'd like you to think about as you hear this is, well, yes, this is going to be Chrome specific, but the thing is, start challenging those assumptions that maybe you've got built into you of, oh my God, I can only do these 2 things. Start going, hey, does this change that demo that I tried the other day? Maybe I'll try it again. Maybe this will be fun this time. So the first thing we did is we moved input to where it belongs, on the left here. Just put it where it is. JavaScript says that there's window.onScroll. Let's try to get the world back to a place where window.onScroll fires, and it fires after you have window.touchBegin, for instance, right? And maybe we could even make prevent default behave sanely. So we started doing that, and Chrome 37 includes this new touch model, and it's very close to Mozilla's, actually. We don't think it's 100% there, but it's a lot more rational as far as input is in the right place. And sort of related to that, we changed the timing and all the machinery that drives both request animation frame and on scroll. It used to be that if you position stuff, I alluded to this, if you position stuff in on scroll and you tried to scroll at the same time, you'd see them sort of never quite line up. And we did a lot of tweaks so that if you stay within a 16 millisecond budget, you can do on-scroll positioning. So you can do sort of a ghetto position sticky now, or a ghetto pull to refresh if you pair the input changes we've done, or a couple other things. And we're aiming for even bigger there, but this is sort of the first thing. Now we also did just, I guess you could call it a spring cleaning of the code. When we began the project about a year ago, we were really worried that like the web was insolvably fast. Unsolvably fast? Slow. Basically, we were worried that CSS is algorithmically impossible to do at real time. Because in CSS, you have a thing where you have n selectors and m elements, and you have to sort of cross-product them to figure out what matches. And this is just sort of n times m. It's a big number. Oh, my God. And similar around layout. Like layout has so many intricacies, floats, line management. Like it's hairy stuff. And so we were really worried that this second box, the recalc, would just be, and the layout would be impossible to do at 60 FIPS. And we dug, and we had a couple crises of faith. And we basically found that the reason that this was slow in all the Chromes and all the WebKits that preceded us was because of some bugs. And just some unoptimized code and just sort of the accretion of big software. And when we fixed it, we found 5, 10. We found optimizations and wins that were just kind of mind-blowing. And we did the same in the compositing stack and found a lot of performance wins too. So this spring cleaning that we did essentially just sped up Chrome's sort of 2 of these critical paths by some, what for us, for graphics engineers, are some pretty neat numbers. So we did one final thing, which is, oh my God, fast painting. So if you've studied painting and you've studied hitting 60 FIPS, we always say, oh my gosh, don't paint. Whatever you do, turn off your, do everything you can to avoid a repaint, because repaints are catastrophic. And that's true, but it also stinks, right? Because you want to paint. You might want to show something new, and then you got to paint, right? So why does that have to be a mandatory jank? So the technique that we wanted to bring out to fix this is GPU rasterization. GPU rasterization is just where we use the GPU to fill in the pixels on the screen before we make the layer. So we've got a layer and we've got to fill in the pixels in it. So if you have a white layer and a border, then that's a draw, like a WebGL draw with the triangles for the white, and then some more triangles to represent the border. For many cases, like simple content, the GPU is way, 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 way faster than we can ever do with the CPU. But it sort of falls over when you start throwing like Gmail at it. And there's this other pesky problem, which is like when you used to run this on an old Samsung phone, the phone would just reboot when you went to certain pages, which gives you a really bad page load score. So we were really conflicted. It's like, well, this is so much faster, but the time that we're going to need to get this working perfectly on every device for every piece of content, make it really good for Gmail and really good for mobile content, is, you know, heat death of the universe. So we settled on something that is kind of awkward, but gets the content, the capability into people's hands. And we call it the magic viewport. If you put this viewport on your content, and you have a phone that we've enabled, we've tested and we've verified that your phone doesn't reboot, which is, you know, a good thing, we will give you GPU rasterization instead of the CPU rasterization. And I have the understated sentence, goodness results. So demo. It's not a very interesting demo, per tradition. So what I'm going to do is show you the content, and then we'll come back to my screen to show you the numbers. So this is just, what we're going to do is we're going to look at this piece of content, which is just an image that is animating its width. There's no transform kerfuffle here at all. We are literally animating the width and the height of an image. If you look really carefully, you can see there's a drop shadow on the right of the image that stays nice and crisp as it animates up. There's a 1 pixel border around the image. This is the kind of thing that you can't do with scale animations. And you see stuff like this that's prettier when you tap a contact icon on a phone and the icon grows to be a picture of the person, right? And it looks gorgeous and you ooh and ah. That requires repainting every frame. And this is something that is really, really costly in the old painting architecture. In Chrome 37, you can measure this without the magic viewport. And what you'll see is these paint times are obscene. So we're looking at 50, 60 milliseconds. That does not a frame make, right? 16, it's 3 or 4 frames. Now it looks decently smooth when you see it on the projector, but it's just, we're paying dearly for this look. So if we, somewhere in here, I have magic viewport.html. And the only difference in this is we put in that incantation. And so if you look at this one, I'm not going to show you, it's the same darn thing on my screen. The trace looks completely different, right? Those bars are much, much smaller and everything is hitting 60. The frames are 16 milliseconds. This is really good. And what's happening here is the GPU in this case is just killing it as far as performance goes. So the magic viewport enables sort of this future technology that we eventually want to see throughout the Chrome ecosystem. And this gives you early access to it if you want to be sort of dog-fooding it or trying it out. Now, of course, there is this restriction on your machine, but if you want to do some experimentation, you can force GPU rasterization and it'll turn on. Okay, so pause. We've been opinionated about this is kind of weird that we have to do all these layers, and then we talked about what we've been doing so far to hit 60 FIPS. And the message that I'm really trying to communicate is we actually think we're getting somewhere where you can actually hit 60 FIPS pretty easily and not kill yourself. Now, if you want to be guaranteed that you'll hit 60 FIPS, you still want to invoke the old transform, translate, be very careful mechanisms. But in Chrome 37, and probably much more as we proceed with our relentless update cycle, you will see that you can run each and every one of these stages and have them firing every frame and still totally hit 60 FIPS. And what we're working toward is a way that you can think about performance in sort of a completely rational way. Instead of having this weird voodoo that like Paul in the back understands and I sort of, you know, quarterback poach that, we want a model that's completely understandable and everybody can fit in their head. And this is sort of what we got in 37. There are two parts to the performance model. First, you want to think about what pipeline stage you're going to trigger running. So if you change the width of something, then the recalc and layout system is going to run, and then it's going to trigger everything down in the pipeline. But if you change transform and opacity, only the bottom stage, the composite stage, is going to run. Now you'd think, hey, this has been the case in browsers since forever, except bugs. Big browsers, big software, and it turned out that even recently, when you mutated opacity, if you did it in the wrong way, you would actually cause the whole darn stack from recalc to run, and you'd end up with repaints, and you'd be sitting there going, I don't understand what's going on here. So we're cleaning this up. We're making this part of the mental model completely clean, that if you mutate one of these properties, you will get a predictable set of things that run. And CSS triggers lets you sort of reason about that. There's another half to this model that we're working on too, which is to give you sort of this relatively easy to grab a hold of mental model for how long each of the steps of the pipeline takes. Now the reason for this is, once you can say, oh yeah, composite is proportional to such and such, you can build up a budget in your head of how much time you want to spend in each one of these stages when you want to burn out your 16 milliseconds. So you might say, I want to spend most of my time in recalc and paint, but I want to like composite. And once you understand what causes each of these stages to run long, you can then tweak your content to control it. So the composite, for example, is proportional to the number of layers. So if you have about 30 layers, you're looking at 3 milliseconds-ish on Chrome per frame of cost. And if you double the layer count, then it'll go up, etc. Painting is basically proportional to how much area-wise you change times what's in it. So a white square is going to be quite a bit cheaper than a square full of all sorts of text that has a drop shadow and a border and a filter on top of it. It's pretty straightforward. So, you know, a solid div, sort of free-ish. And of course, if you have GPU rasterization, you get sort of this, you know, extra boost, right, that hopefully we'll give to everybody really soon. Recalc and layout is an area that we're just beginning to poke at, so I don't have a really clear message here. What we do know is that you definitely shouldn't style thrash. So you shouldn't set the styles on something and then try to read them back by getting computed style. If you do that, then you're basically killing yourself. And a really common mistake that we see people do is in trying to make make CSS transitions work for them, we see people having to force recalc and everything goes to hell. The fix for this is to use web animations. It's fantastic. But if you eliminate sort of the basic mistakes of not thrashing, then the mental model that I think we should use for now is that the cost of recalc and layout is basically proportional to the number of elements in your DOM. Not visible elements, total. So if your DOM is 1,000 elements, which we think is about a good match for mobile phones, you can run substantial portions of recalc without all of a sudden falling into no FIPS territory. And of course, if you reduce that count, you'll go even faster and so on and so forth. What's right out is a 10,000 element DOM on a mobile phone. Just don't do it. Start figuring out how to reduce that. Use viewporting, use whatever you want, but keep your element count down because the purple stage is proportional to element count. And finally, contrary to some really weird press articles and research articles, so-called, JavaScript is ridiculously fast. And GC is rarely a problem. The web is not slow because GC is the problem. The web is slow because we didn't optimize recalc, layout, paint, and composite. And because the model is kind of broken about only being able to do layers. GC is in the noise. When we do see JavaScript run long, the few times I've really dug into it, it's usually just because the JavaScript is making a lot of DOM that it's going to append to the worlds for your rendering. And we know the solution for that. That's to use templates if you can, because templates allow us to amortize costs and do things a lot faster. We know a lot about the composite step. we want to firm up this sort of model and make it really easy to communicate. This is the first time we've tried explaining it. Hopefully this will get cleaner and cleaner over time so that everybody can just immediately go, oh yeah, you're animating width. Well, how many elements do you have? Oh, okay, you're good. You're good. You can do that. So anyway, with Chrome, you really can these days hit 60 FIPS. So what I want to do now is try to explain sort of the logistics of how to put this together. Because what we see a lot is people just slap in animations and transitions all over the place and sort of hope for the best, which I totally get because like some days you just got to get it out the door. The really great transitions happen when the people writing them plan the whole transition as the set of animations running as sort of an effect. So when the finger comes up, you look at all the things that you're going to want to move and you get them all ready to go. You do any DOM creation that you need to do for all of the things that are going to need to move, and then you get them all going at once. And you do your nice animation, and then later you do some cleanup, like maybe you tear down the old DOM. And in the middle there, you try to keep things relatively clean because you're trying to give the system as much opportunity to just make frames smoothly as it can. Now there's two really, I think, surprising things about these sort of transitions. The user perceptually isn't going to start complaining that you're laggy when you lift for about 150 milliseconds. That's a lot longer than 16. So you can do some substantial amount of DOM creation right after finger up and still have people say, oh yeah, your app is great. And Topeka, for example, this thing that I showed, this does a lot of DOM creation. So its finger ups are actually quite long, but you don't notice it. So let's mentally work through this situation where you want to have, you want to have a card that you tap, and it's going to go to the server and get some data, and then come back and make some DOM, and then you want that to appear, right? A really great way to structure this is to, even as you kick off the XHR, you start an animation right away without the content. Make the card. So you saw in Topeka, that initial demo, you saw the yellow card grow. You can get that going and have the visual response going right away. This gets the user feeling like you're responding to them, even though you don't have the XHR back. And then you can use sort of some web animations and CSS animations magic so that when you do create the DOM, you don't get any jank. So let me show you why that is kind of useful. Two soccer balls, they're both rotating. The left one is a CSS animation that we're running. It's a rotate, transform rotate, right? The right is just RAF spinning in JavaScript. They both can hit 60 FIPS. They're basically both about the same speed. But if I introduce jank on the main thread, then what happens is the JavaScript-driven one starts feeling kind of juddery. And the reason for that is because the CSS animation is running off thread. It's running where we do that scrolling. So just like how we were able to scroll smoothly, this is a case where the CSS animation and all this compositor machinery is actually kicking in and saving the day. So when you bring this back to the demo that we're thinking about, when you do something where you're expanding a div to give a user a sense of appearance and responsiveness, if you do it with a pure transform and scale animation, you can have a party on the main thread creating DOM in the background in response to an XHR and still stay completely smooth. So the user will experience this as a great smooth animation, even though you have two substantial janks, one for the finger up and one for the create DOM. But there's this sort of contract here again, creeping up on us, right, that I talked about at the beginning, which is, can you represent the thing you want to do with a pure transform and scale? And the answer is, well, yes, if your cards are material design, right, and you're lucky enough that all your things are just flat with no borders and no drop shadows, for instance, great, you're good. But if you're unlucky and you want a border around this, then all of a sudden you can't do transforms. You need a width and height animation. With sort of the newer builds of Chrome in 37, et cetera, this is still totally possible. When you have GPU raster, the paint isn't going to kill you. And because we've sped up all these individual steps, you can now get your XHR back, maybe hold off your DOM creation, but then with a RAF loop, actually tick that height and width yourself. And you can even run, you could decide, oh, I want to use a width animation in one direction, but I want to use inner margin as my other animation key, and it'll just work. And so then you can stage this and sort of play games so that you keep the main thread responsive the entire time, but you are, and by keeping the main thread responsive, you're able to do all sorts of sophisticated animations using the stuff like height and width and so on. Anyway, this is like bleeding edge. We envision that in the future, we can essentially return to the way you did animations with jQuery long ago, which is you'd say, $blah, blah, blah, dot anim. And it would just, you could pick any CSS property and it would be smoothish, right? We want to come back to that and not have to say, no, please decompose your animation into these two properties. That stinks. So the same sort of thinking applies to touch. Pull to refresh, right? We use it every day in our mail apps, in Twitter, in social apps. It's built into the mobile experience, but it's very hard to do on the web. And in fact, the way people do it is you do something like iScroll that just hijacks scrolling from the browser. Where we're going is we're trying to make it possible to do these touch-driven effects at 60 hertz with a touch move coming right in. You do all your processing of the touch move, and then you do a composite, and it just runs at 60 FIPS. There's some people who say that the way to solve this is to add a feature to the web platform, like a pull to refresh widget. Frankly, I don't think we should do that because we'll screw it up. We won't hit every case. Better to empower JavaScript to do this and then let individual library authors make great widgets. And the way to do that is to have a sane cost model and then have a sane place where input is delivered, and then just let JavaScript run. And to give you an example of this working, this isn't pull to refresh, this is another widget. This is a Heidi bars widget. So you can see these gray things coming in and out as I scroll up and down. In older Chrome builds and in most browsers, especially IE when you do this, the scrolling is not coordinated with the bar appearing. They just sort of race with each other. And we worked really hard to make sure that if you stay responsive in JavaScript, this will appear coordinated. So this gives you a lot of flexibility to then do whatever effect you want that's scroll coupled. You can do pull to refresh too. I'm not going to get into that. It's pretty cool though. Final segment. So, we haven't really been shy on opinions here, right? Or I haven't been. We're going to keep at this, and we're always going to make the translate and transform based effects super, super fast. That is sort of our bread and butter. We'll always make that work. But where we're headed is to double down on this sort of, we want to make the full richness of HTML also able to hit 60 FIPS. But before we do that, we've got some basics to attend to. This GPU raster thing, the Magic Viewport's pretty cool. We want to make it work all the time without the Magic Viewport, and we're gonna get to that. It's just sort of turning the crank, fixing a lot of bugs. We know that there's a lot of dark, unexplored corners in the platform where things don't quite work right. And a good example is the pinch viewport. When you pinch zoom, position fix behaves really weird, and so you get all these bad behaviors. We want to fix that. We want to make just when you have a mobile app, it just sort of works. And the old pinch model doesn't mess you up. And of course, we're always working on tools. You saw there's new stuff coming in DevTools. You saw the frame viewer. That's eventually going to show up in DevTools, so you don't have to use that tracing tool. Cool stuff coming there. But really that bread and butter, or above that, we're going to be pushing this and pushing hard. We're going to try to make it possible to animate new kinds of things, and we're going to try to make it possible to do finger-coupled effects without all sorts of voodoo. And this is really all about empowering JavaScript, right? We think that having this compositor thread that is the only thing imbibed with the ability to scroll is crazy. And we also think that when you have that model, you can't have a clear, what's fast, what's slow. We want a clear class model. Anyway, this is where we're going. I think what I want to do is wrap up. As you go back to your computers tomorrow, the next day, and you sit down, dig through some prototypes you did last year or last week, and try it on our latest builds, on Canary, on the beta channel, on Chrome Android. See if it's still slow. And if it is, keep some of this in mind. Let us know what you think. And then, start questioning these fundamentals and say, okay, I want my app to work like this, and file bugs against us and say, I want it to work like this. Chrome, can you fix it? And we'll be listening. So anyway, that's what I have to say for all of you. Thank you for listening. And I guess time for questions, I suppose. Yeah, how do we want to do questions, Paul? Do you want to MC?
We can try.
Yeah.
I reckon we've got time for just 1 or 2 questions. Hands up. Oh, okay.
So traditionally in all browsers, rounded corners with a small shadow has been expensive. Does GPU rasterization or compositing, whichever it was, make that a lower cost operation?
Yes. Different things become the good thing and other things become the bad thing. So I believe the verboten thing at the moment on our GPU raster architecture is lots of fonts with different sizes. That's the thing that makes it grumpy. This stuff changes a lot. The rounded rex was particularly bad. The key thing with the GPU raster is it just takes it from this catastrophic number down to sort of a 4 and 5. So now you're instead of looking at, oh my God, I've got 300 milliseconds of paint. Kill the rounded corners because it'll get it to 200, right? Now you're looking at like, are we going to argue about 2 milliseconds? And sure, we can argue about 2 milliseconds, but it's in a better and more sane place. It's more in line with the other pipeline stages. And that's what we really want to do.
We're going to have to wrap up for time. Thank you, Nat.
Thanks, everybody.